Hi there, my name's Ian Candy and I'm a Professor of Physical Geography here at the Department of Geography, Royal Holloway, University of London. My area of expertise, the area I research in, is in climate change. In particular, I'm interested in how climate's changed in the past, how climate's changed naturally, and how we can use that to help us understand what's happening now in terms of climate change and the climate crisis at the present day. In particular, the role that many geographers play in trying to understand climate change is understanding how climates vary naturally, what causes them, what timescales they change over, and how what's happened in the past is different from what's happening at the present day, and that difference being due to humans. And what I'm going to talk about today is just a little bit about why understanding what natural climate change is so important to the current debate about the climate crisis. So I'm going to focus on how do we know that what's happening now is because of humans and it's not just part of some natural climate cycle similar to those that have happened thousands of times in the past. Now, if you study geography at university, climate change is a subject that you'll deal with on many different levels. From a physical geography point of view, we'll talk about the science of climate change, the way that climates change naturally, human impacts, and the impacts those have on the way that the Earth system operates. On a more human geography side, you'll deal with the societal impacts of climate change, the impacts on communities, on economies, on livelihoods. Undoubtedly, regardless of what area of geography you focus on, you'll come into contact with something known as the IPCC. This is the Intergovernmental Panel on Climate Change. And the IPCC is an international body of climate scientists who work together to collate science of climate change to synthesize our current understanding of the way that climate is changing and its potential impacts on the future. Really what they're trying to do is to summarize this science for policymakers so that governments around the world have an awareness of what might happen in the future and what they need to plan for. Well, the first IPCC report, the first assessment report, was published in 1990, and then a series of reports have been published until the assessment report 5, which was published in 2013. And our understanding of climate change has really developed over the years with more and more science, more and more ideas, more and more studies coming together to really allow us to understand what's going on with the climate system. And I guess the crucial take-home point about what the IPCC has found is that over the years, the scientists who work within the IPCC have become more and more convinced that one, climate is changing, and two, climate is changing because of human activity. And what I'm going to highlight over the next few slides is really just some quotes from the IPCC which show that. Okay, so how has the IPCC's view on human impacts on climate change changed over the years? Well, this is a quote from the third assessment report, which was published in 2001. Most of the observed warming over the last 50 years is likely to have been due to the increase in greenhouse gas concentrations. Now, when the IPCC uses a term like likely, it has a statistical probability behind it, and likely means it's 66 to 100% certain that that is the case. Okay. Now, the crucial thing about this is this quote talks about warming and it links it to greenhouse gas concentrations. It's showing that greenhouse gas concentrations have been causing warming over the last half of the 20th century. It doesn't really mention humans there, so it's not necessarily ascribing a cause to the source of those greenhouse gases. It's just highlighting that warming is occurring as a result of increasing greenhouse gas concentrations. When the fourth assessment report was published in 2007, there were some changes to the views of the IPCC. Most of the observed increase in global average temperatures since the mid-20th century is very likely due to the observed increase in anthropogenic greenhouse gas concentrations. Two changes from the first quote. Firstly, very likely, so much more confident, 90 to 100% certain that this is the case. And also the use of the word anthropogenic. Anthropogenic means humanly generated. So it's not just saying now that the warming over the later part of the 20th century is due to greenhouse gases, but those greenhouse gases have come from human impacts. And most startlingly of all, the fifth assessment report published in 2013 made a very clear statement: human influence on the climate system is clear. It is extremely likely, notice extremely likely, this means 95 to 100% certain, that human influence has been the dominant cause of the observed warming since the mid-20th century. So the IPCC has gone from acknowledging that the climate is warming and it's due to greenhouse gas concentrations to a situation where they're very confident that that warming is due to human activity releasing those greenhouse gases. Now, as somebody who studies past climate change, I'm fully aware that climate is always changing. Climate's never stable. It doesn't matter whether you're talking about hundreds or thousands or tens of thousands or hundreds of thousands of years. Climate change is the natural state, not climate stability. So why is the IPCC so certain that what's happening now is because of humans and it's not just part of some natural climate cycle? And that's really what I want to focus on this talk. Two key questions, okay? Why is the warming over the 20th century different? Why isn't it just like any other cycle of climate change which has happened many times in the past? And if is it due to greenhouse gas concentrations? Why are greenhouse gas concentrations now? How are they any different from changes in greenhouse gas concentrations that have occurred in the past? And these two questions I'm really going to discuss over the next few slides. Okay, so this idea about how unique is warming across the 20th century is key to global warming science because it's long been known that over the last 2,000 years, climate has changed. Climate has gone through natural cycles of warming and cooling. Two of the most famous warming episodes are the Roman warm period from about 250 years BC to about 400 years AD, and more famously, the medieval warm period from about 950 years AD to about 1250 AD. These are periods of time where we have historical documentary evidence that the climate, certainly in Europe and the North Atlantic, was warm. Some people would argue at least as warm as the present day. One of the most widely cited lines of evidence for this is wine production in Britain. So wine production, grape growth obviously requires warm temperatures, and during both the Roman warm period, but more famously during the medieval warm period, you had extensive wine cultivation, grape cultivation across southern Britain, central England, and northern England. Other lines of evidence are, of course, the Viking colonization of Greenland during the medieval warm period. There was a successful and stable Viking community in Greenland. As the medieval warm period came to an end and climates began to cool, Vikings abandoned that area and these settlements became empty. And many people have long argued that even if warming is occurring during the 20th century, we know that we get these cyclic periods of warming. The 20th century warming is no different from something like the medieval warm period. And of course, just as we have periods of warming, we also have periods of cooling. The most famous of these is the Little Ice Age, from about 1350 years AD to about 1850 years AD. Lots of very famous paintings here showing Europe in the snow, testifying to the much colder conditions. So things like frost fairs on the River Thames, when the Thames would freeze over and it was cold enough for markets and fairs to be held on the Thames. These are very, very common features of Europe from 1350 to 1850. Well, if we know that this climate change is occurring a lot in the past, why are scientists so convinced that what's happened during the 20th century is different? And one of the big problems of these questions, and actually one of the greatest sources of uncertainty when we think about climate change, is that we actually have very poor long records of climate change. If you think about weather stations, temperature variations recorded using thermometers, okay, which are the most accurate way of most people would say of recording temperatures, most of those records only go back 100 to 150 years. What I'm showing you on the screen here is the longest instrumental record of climate change anywhere in the world. It's the Central England temperature record, and it goes from about 1770 to up through to the present day. Now, the problem with this is if you're trying to understand how humans have changed climate, and most people would argue that really began about 1750 with the Industrial Revolution, you need climate records which go beyond the start of human impacts on climate. And this is our longest instrumental temperature record anywhere in the world, and it doesn't even go past the start of the Industrial Revolution. That means that we don't really have any instrumental records telling us how warm the medieval warm period was, whether it was warmer than the present day, the same as the present day, or cooler than the present day. That means everything that I've talked to you in terms of climate cycles over the last 2,000 years is really based on qualitative, as in non-quantified evidence. And so actually trying to understand how the 20th century is different from periods in the past is really problematic. And this is why researchers have tried to reconstruct climates beyond the instrumental record using different lines of evidence. And this graph I've got on the screen now is really one of the most famous climate curves or climate graphs anywhere in the world. It's known as the hockey stick curve, and it was produced by Michael Mann along with a large number of other researchers in an attempt to produce longer quantified temperature data sets. And what this shows, so the y-axis, the 0 is climate average conditions between 1961 and 1990, which is quite often used as our climate baseline. When the graph is below that, it means the climate at the time was cooler than that 1960-1990 average. And when the line is above that, it means it was warmer than that time interval. And the red part of the curve, the red line here, this is temperature reconstructed using weather station data. So this is instrumental or thermometer-based temperature records. And the blue line is temperature reconstructed using other lines of evidence. How do we reconstruct temperatures when we don't have weather station data? Well, we use things like tree rings, we use things like ice cores, and we use things like corals. All of those grow incrementally. So tree rings, each season you have another growth of the tree. Ice cores, ice stacks up vertically on top of the dome of the largest ice sheets in incremental yearly layers, and corals grow yearly, so they also have yearly bands within them. And different aspects of tree rings, so the width can tell us about the strength of the growing season. Ice cores, the chemistry of the ice can tell us about the air temperature, which was in existence when snow fell. The corals, the chemistry of the corals can tell us about sea surface temperatures. All of those allow us to quantify temperatures, even though we don't have instrumental weather station data. Now, one of the things that Mann and researchers have always highlighted is when the weather station data, the red line, and what we call the proxy data, the blue line, overlap, they match one another very nicely. And those researchers have always used that as evidence that their reconstructions in the past are valid. And what this line shows us is just how different temperature warming in the 20th century is from any form of climate variability which has occurred over the last 1,000 years. Sure, the climate of the last 1,000 years has varied. You've had warmer periods, you've had colder periods, there have been fluctuations, but none of them are comparable to the warming which has occurred over the 20th century. And what this record shows us very nicely is that we do have a medieval warm period. We have a period from, so 1950 AD would be just before that, 950 AD would be just before this, so about 1300, 1250, warmer conditions. Then we move into the Little Ice Age and we have cooler conditions, but the medieval warm period is nothing like the 20th century. The 20th century is much warmer, and it's also characterized by a much more rapid rate of warming than anything we see in the last 1,000 years. So the 20th century, if we consider the last 1,000 years as a time period, the 20th century is unique in terms of both the magnitude of warmth and the rate at which warming has occurred. So we can look at the past and we can say, yeah, sure, we have warming and cooling cycles, but they're really different. Yes, in the last 1,000 years, climates have fluctuated significantly, but the magnitude of that warming which is currently occurring is unknown in the last 1,000 years, and the rate of warming is unknown in the last 1,000 years. What we're dealing with in the 20th century, moving into the 21st century, is unique for the last 1,000 years. Now, Of course, a lot of this is subscribed to greenhouse gas concentrations. The IPCC, in those quotes I gave you, have stated that the warming is due to greenhouse gas concentrations and that greenhouse gas increases relate to human activity. How can we be sure of that? Because all of the problems that we've talked about in terms of understanding climate change in the past are doubly true for carbon dioxide. Because to understand how carbon dioxide concentrations have changed in the atmosphere, we need to have a measured record of atmospheric concentrations of carbon dioxide. And actually, we've only been measuring quantified carbon dioxide concentrations in the atmosphere since the late 1950s. And this is the CO2 Observation Centre at Mauna Loa. And effectively, you can see that it was started in the 1950s and recorded over the second half of the 20th century. But what was happening before that? You can see this very clear trend. So we're measuring carbon dioxide concentration in parts per million, CO2 parts per million in the atmosphere. And you can see that carbon dioxide varies seasonally. But since the late 1950s, there's been a very clear upward trend. Average concentration in the late 1950s, around about 315 parts per million. By 2000, it's 370 parts per million, so it's gone up by 60 parts per million. Now it's about 416 parts per million in the atmosphere. But is that unique? Is that different? Is that wildly higher than it's been in the past? Is that rate of change different from what we've seen in the past? How do we know whether carbon dioxide variations that we're seeing over the later part of the 20th century are different or unique? And again, this is where ice cores are so important. So ice cores have been taken from the largest ice sheets on Earth, from the Greenland ice core, from the Antarctic ice sheet. And effectively, snow falls on the top of the ice sheets. It stays there. More and more snow lands on top. It compresses it into ice. And if you take a core from the highest point of the ice sheet, that means that what you're getting is a record of ice going back through time. And as well as that ice being able to tell us about temperature, as the snow falls between the snowflakes, you have air. And that air is recording the composition of the atmosphere at the time that the snow fell. As that snow becomes compressed, that pockets of air become sealed air bubbles or gas bubbles. And effectively, when you have an ice core, you take sections of the ice, you melt it, you measure the concentrations of the gas which are trapped in those ice bubbles, those air bubbles, and that tells you the concentration of the different gases in the atmosphere at the time when that snow fell. And this allows us to reconstruct greenhouse gas concentrations going back thousands, tens of thousands, even hundreds of thousands of years. Well, the longest ice cores come from Antarctica. This is taken from a graph. This is taken from the third IPCC report published in 2001. At the time, the longest ice core from Antarctica went back about 420,000 years. About 15 years ago, a new ice core record was published, which goes back 800,000 years. But the pattern that those ice cores record in terms of greenhouse gas fluctuations is nicely illustrated by this figure here. So we're going back in thousands of years here. So this is the present day, 100,000 years, 200,000 years, 300,000 years, 400,000 years. And this is showing variation in CO2 in the atmosphere. And the first thing that you can see is very clearly, yeah, greenhouse gas concentrations change a lot. CO2 varies a lot in the past. Periods of time when the world was in an ice age, you had relatively low greenhouse gas concentrations, round about 180, 190 parts per million. So every ice age we get down to about 180 parts per million of carbon dioxide in the atmosphere. Once you leave an ice age, you get this very rapid increase in atmospheric carbon dioxide, and you get up to about 280, 290, in some cases around about 300 parts per million. So between an ice age and the warm periods between the ice age, which we call interglacials, you get at least 100 parts per million difference in CO2 concentration variability. CO2 in the atmosphere varies a lot in the past, and we know this. But what's astonishing is how different carbon dioxide concentrations in the atmosphere are at the present day. Because this is how what's happened over the last 1,000 years matches on to what's happened in the past. Most interglacials, the warm periods between ice ages, you get between 280, 300 parts per million of carbon dioxide in the atmosphere. At the present day, we are over 400 parts per million. We are more than 100 parts per million higher than we've seen in any interglacial of the last 800,000 years. And what's really telling is when you focus in on the last 1,000 years, because this graph here at the top focuses in on the last 1,000 years. And 1,000 years ago, medieval warm period, atmospheric CO2 concentrations were about 280 parts per million, exactly what we'd see in almost any natural warm period in the past. And those CO2 concentrations stay at 280 for most of the medieval period, going into the Little Ice Age, and then about 1750 they start trending upwards, and then they accelerate across the late 19th century and accelerate again across the late 20th century, moving up to levels beyond that which we've seen in any natural warm period of the last 800,000 years. And the amount of CO2 in the atmosphere is really shocking when compared to these past warm periods. More than 400 parts per million. That's 120 parts per million greater than any natural warm period of the last 800,000 years. But it's not just the magnitude, it's also the rate of change. Because between an ice age and an interglacial, you frequently see rises in carbon dioxide of about 100 parts per million, but those rises occur over many thousands of years. In our current situation, we've had over 100 parts per million increase in carbon dioxide, similar, therefore, to what we'd see during the rise from an ice age to an interglacial, but that rise has occurred in only 250 years. So it's not just the amount of change, it's the magnitude of change, it's the rate of change, which is truly different from anything we've seen in the past. So current levels of CO2 in the atmosphere are unique for the past 800,000 years, and the rate of 20th century carbon dioxide is also unique for the past 800,000 years. And what's noticeable from these records is that the onset of this acceleration in CO2 in the atmosphere corresponds with the start of the Industrial Revolution. Now, this is probably the most complicated diagram I'm going to show you today. Effectively, all this is showing is energy changes, so the amount of energy that the Earth is receiving in watts per meter squared from as a result of changes in different variables. Because if we forget greenhouse gases, the two main ways that climate will change is because of volcanic activity, and that's the top line here, and sunspot activity, which is the line here. And you have periods of pronounced volcanic activity when the Earth gets a bit cooler, less volcanic activity when the Earth gets a bit warmer, less sunspot activity when the Earth gets a bit cooler, and more sunspot activity when the Earth gets a bit warmer. But the important point here is that over the 20th century, volcanic activity and sunspot activity have really been cancelling each other out. If it was just down to volcanic activity and sunspot activity, our climate would be stable. It wouldn't really be going under much increase. You effectively would have very little temperature change. To produce this warming that the hockey stick curve shows so clearly, you need another variable, and that variable is greenhouse gas concentration. So, to summarize, the current warming is unique in the context of the last 1,000 years. If we think about the amount of greenhouse gas in the atmosphere, again, we're in a unique situation, not just compared to the last 1,000 years, but compared to the last 800,000 years. Only greenhouse gas warming can explain the temperature rise over the last 150 years. and the level of greenhouse gas in the atmosphere can only be explained by human activity. And that's why the IPCC is so confident that what we're seeing at the present day, the warming that we're seeing, is a result of human activity.